Hello, I'm David Towers and I'm here to give you a brief overview of our paper that's been accepted in CVPR, Insights from the Use of Previously Unseen Neural Architecture Search Datasets. The first thing I want to do is just to give a brief list of the 8 datasets that we created in our paper, and they are AdNIST, Language, MultNIST, Gutenberg, CipherTile, Isabella, Geoclassing, and Chesseract. Our motivation for creating these datasets comes from the fact that in NAS, generally, 2 datasets are used to evaluate most modern algorithms, ImageNet and Cipher10. While these datasets are definitely useful, we feel as though that this is going to create some sort of overfitting where instead of having NAS methods that can create good architectures, they only create good architectures for the 2 datasets. So we created the Unseen Data Competition, and through this competition we've created 8 datasets which are previously unseen, and we're now releasing so that they can be used to benchmark NAS methods and other methods that would want more data. Our hope is that we will improve the generalizability in NAS and other fields. For more information on the datasets, please go see our paper, although I am going to give you a brief overview of each of the datasets that we've created. We created these datasets with 2 types in mind. The first type is a task that a human could easily solve. An example of this is our AdNIST dataset, where simply you sum up the numbers in the channels and minus 1. If a machine learning task can't solve this, then what's the point? We want a human to do it. We want machine learning to at least be able to do what a human can do. The second type of task is something that would be very hard for a human to do. So this is like our geoclassing dataset, where you need to identify which European country the photo is of. And this is a lot harder if you're not familiar with this sort of topology. Moving on to the datasets themselves, we'll start with AdNIST, and AdNIST is comprised of 3 MNIST images in the 3 color channels. Now, instead of just normal classification, we have a formula, which is the sum of the 3 channels minus 1, which we hope that the algorithm needs to figure out. So it's not just simple classification, it needs to figure out that there is a calculation to perform. And that is what we want to see with this dataset. We want to see whether machine learning could identify a calculation was needed, rather than just pure classification. Now, our second dataset is the language dataset. Now, this is created by encoding 4 words from a given language's dictionary that are all 6 letters into a visual space. And the task is to identify the source language. We want to see whether or not this type of visual encoding gives enough information for machine learning to identify the language. So MultNIST is very similar to AdNIST, but instead of summation, use multiplication. The 3 channels are multiplied together and you take the last image. Now this solves a problem that AdNIST has, which is that high numbers mean that you can't have any of the lower classes. Because we are doing multiplication, this is not necessarily the case. And because of this, MultNIST actually asks the same question that AdNIST does, but potentially does it a little bit better. CipherTile is a combination of 4 Cipher10 images, and the task is to calculate the number of unique classes. So the example images, there's 2 elks, a plane, and a horse, so that would be 3 unique classes. This is going on our theme of making it do classification, but getting it to do a little bit more. So instead of just simply classifying what the image is, we want it to count the number of classes that it has predicted. Gutenberg is very similar to the language dataset, but instead of encoding words from the languages, it encodes a phrase from a book. And the task is to identify which author the book that the phrase comes from belongs to. Now, this is very similar to language, and that includes its research question, because we want to see whether or not the information that the phrase contains can be identified by a machine learning model, and more to the point, can be identified from an image representation of that string. Isabella contains a collection of spectrograms from musical pieces, and the task of the Isabella dataset is to identify which period these pieces belong to. Spectrograms contain a lot of audio information, so we wanted to see whether or not a machine learning model can decipher this information from this visual representation. Geoclassing is made up of satellite images of 10 European countries, and the task is to identify which country the image belongs to. We want to see whether NAS could identify the subtle changes in topology, foliage, and things like that to determine which country that the image belongs to. Chess is a collection of Grandmaster chess endgames, and the task is just to predict the outcome of the game. Chess engines such as Stockfish and Altzira already employ machine learning to not only predict who's going to win, but the optimal moves to that win. We just wanted to see whether a visual representation of the board is enough for a machine learning model to predict who's going to win. This table shows the best results that we have found from our CNN experiments, our NAS experiments, and from competition participants. It's sort of a baseline across each of our datasets. If you want more details into the CNN results and the NAS results, please check out the full paper. We also provide some more analysis into this. Our hope is through the release of these datasets, we will improve the generalizability of NAS and encourage the creation of other datasets. Thank you very much for listening. That is almost all from me. For more information, please check out the full paper or follow the link on the slide or the QR code to go to our GitHub. Thank you very much.